Okay, so we're going to talk a little bit about the fundamentals of gas detection. If everybody can hear me okay. Why we use gas detection, the type of gas sensors, how a system even works, our three-step approach to solving gas detection applications, and then into some applications, and then some questions and answer period time. So why we use gas detection? First and foremost, to protect lives, protect people. And second, to protect property. We protect people by monitoring toxic gases, exposure limits, and making sure that we bring ventilation on so that people aren't overexposed to those toxic gases. We protect property by ensuring that combustible and flammable gases do not build up to the point where they're dangerous and cause damage to the buildings through fire or explosion. And of course, by using gas detection as a method to control ventilation, we are doing our part for the environment. We're running ventilation fans only when required. We're controlling fan runtime and speed to avoid wear and tear. And we're using minimal energy in reheating or recooling makeup air. And of course, all of that leads to saving money. We're no longer writing blank checks to the utility companies. Now, more and more regulatory authorities are getting involved. I equate the gas detection industry to the fire detection industry in that the fire detection industry has been around for well over a century. The gas detection industry in the commercial and industrial space has been around just a little under 30 years now. And in that 30-year time period, the gas detection industry has brought into effect through various state and local regulatory authorities more rules and regulations than the fire detection industry in the same period of time. So over the next coming while, I don't know, maybe 5 or 10 years, you're going to see even more rules and regulations put into place by authorities such as American Conference of Government and Industrial Hygienists, National Institute of Occupational Safety and Health, Occupational Safety and Health Administration, the International Mechanical Code, of course, and our own industry, ASHRAE, and the environmental protection agencies of various countries. And to give you a bit of understanding of how toxic gases are identified and exposure limits and recommended exposure limits and permissible exposure limits are published out to the industry, it all starts with the American Conference of Government and Industrial Hygienists, who are a volunteer group who look at all the various toxic chemicals and gases and dusts and whatnot that are found in the workplace, and they set exposure limits based on scientific data, scientific and health data. They set exposure limits, which are then channeled to the National Institute of Occupational Safety and Health, who in turn pushes it out through OSHA, the Occupational Safety and Health Administration, of which all our different countries have a version of that organization that gets this information out to the public, such that these rules and regulations are followed and exposure limits recommended and permissible are not exceeded. And gas detection comes into play to ensure that those limits are monitored and action taken when necessary. American Conference of Government and Industrial Hygienists set the threshold limit values, of which a level that is believed a worker can be exposed to day after day for a working lifetime without adverse health effects. Threshold limit values are a model for indoor air quality, and as such, OSHA sets permissible exposure limits. And they're based on time-weighted averages, short-term exposure limits, and maximum exposure limits. The types of hazardous gases that are monitored and regulated by these various bodies include toxic combustible gases, toxic gases, which are measured in parts per million and parts per billion, combustible gases, which are measured in percent lower explosive limit, refrigerants, measured in parts per million, simple asphyxiants, which are measured in percent volume versus the volume of oxygen needed to sustain life, and volatile organic compounds, which are measured in parts per billion and parts per million. And then, of course, there's particulates, which are measured in micrograms per cubic meter. How does the gas sensor work? Inside most gas detectors in the industry, there is a type of gas sensor. And there are various types used throughout the industry. And these types of sensor elements, if you will, they produce a very small electrical current, typically in microamps or nanoamps. The gas detection equipment will take that and amplify it and clean up the noise that's on it and turn it into an industry standard signal, like a 4 to 20 milliamp or a 0 to 10 volt or some type of digital signal. That could be anything from Modbus to BACnet to any of the other proprietary type signaling that is out there in the market today. So these gas sensor elements, and I'm just having a little bit of computer problem still. These little gas sensor elements are very small. I think most of you, if not all of you, have seen samples, but they're approximately a little smaller than a loonie and maybe an inch to an inch and a half tall. And they have an element inside them. This particular cutaway right here is an infrared cell. The ambient atmosphere diffuses through the membrane on the top into the inside chamber of the cell. And in an infrared cell, there's a infrared transmitter that is constantly putting out infrared energy. The ambient atmosphere that is diffused inside that cell, if it contains any combustible gas or carbon dioxide, depending upon what the infrared cell is manufactured for and tuned for, the carbon content in that ambient atmosphere, in that concentration of combustible gas or carbon dioxide, the carbon atoms will absorb a certain amount of that energy. So for instance, if 1 nanowatt was transmitted by the transmitter and only a half a nanowatt was received, then a half a nanowatt was absorbed. And inside the microprocessor in that cell, there would be an algorithm that would calculate based on the amount of absorption you have this concentration of that target gas in your ambient atmosphere. And appropriate action can be taken based on that. So electrochemical cells work under the premise that the electrolyte that's mixed, chemically mixed, and is inside that cell will have its highest reactivity to the target gas it was mixed for. And it will, when it reacts with the target gas in the ambient atmosphere, will output a certain amount of current that can then be taken through an algorithm, and the concentration of the target gas can be calculated as a concentration within the ambient atmosphere in parts per million or parts per billion. Solid state cells, catalytic pelistors for combustible gases, non-dispersive infrared, which I just spoke about for refrigerants and combustible gases, and photoionization devices, which work on the premise of ultraviolet light as opposed to infrared light. These are the different types of sensor cells used within the industry. All sensors have a shelf life. Sensors don't last forever. If they don't have electrochemical cells and solid state cells, if they don't have current running through them for a period of time, they lose their sensitivity. They're no longer useful. Likewise, when they're put into use, they all have a lifespan, including the sensors that work on the premise of ultraviolet light or infrared light. Eventually, the miniaturized LED or the lamp that is used to generate the ultraviolet light wear out. So over the lifespan of the sensor element, it's going from maximum output to minimum output or the day it dies. During that period, it has to be calibrated with some frequency to bring that output of that sensor element into line with your 4 to 20 milliamp or 0 to 10 volt output, or your digital output, whatever that may be.
Hey, Ron.
Pardon me?
Ron?
Yes.
Question is, what are the different shelf lives for the different sensors?
That varies. That varies based on the target gas. So shelf life of a solid state cell may be anywhere from 3 months to a year. Shelf life for electrochemical cells, simply because the electrochemical cell is filled with electrolyte, shelf life for those ranges anywhere from a month to 6 months. Infrared cells and ultraviolet cells may have a shelf life of 1 to 2 years. And catalytic beads likewise may have a shelf life of up to a year. But it depends on the manufacturer, how the unit was manufactured, and the type of gas it was manufactured for. And each and every manufacturer of those sensor cells publishes this data. So this data is available. So whenever you're thinking about having sensors in stock to meet a particular requirement for backup or for add-on to an existing system, you want to look very carefully at the time it would take to get delivery from our factory or from the gas detection manufacturer's factory, and the manufacturer's data in regard to shelf life. And any one of the technical people at any of the manufacturers should be able to assist you with that. And I'm sure that Nathan and his team would have no problem getting that information for you. So now, in a gas detection system, sensor mounting height plays a large part of how you're going to configure and install that system. So for instance, if you're monitoring toxic gases in the workplace, you're protecting humans. And if you're protecting humans, then you want to be able to see, you want your gas detection system to see what are people breathing, and act on that. Act on the concentration of the target gas or possible target gas that may come into the breathing zone because you are protecting people. So 4 to 6 feet above the finished floor, or 1.2 to 1.8 meters above the finished floor. And that takes into account carbon monoxide, carbon dioxide, oxygen, nitric oxide, nitrogen dioxide, all toxic gases in the workplace, measured in the breathing zone. Conversely, if you're monitoring for combustible gases or some refrigerants that may be lighter than air or heavier than air, then your sensors for the lighter than air, of course, are going to be at the highest point of the envelope, or in most cases, what's called the ceiling, or they're going to be down near the floor for the heavier than air gases, such that these gases can be detected and the concentrations identified before they become too much of a problem. And with heavier than air gas sensors, you're going to keep them approximately 6 to 12 inches above the finished floor, such that cleaning equipment or movement of items around the floor are not going to damage them. And an example of some of the heavier than air gases: ethanol, chlorine, ozone, propane, most refrigerants, etc. And in regard to sensor mounting locations, you're going to try and get sensors, especially if you're looking for refrigerants or combustible gases, you're going to try and place sensors where the potential leak may occur. So if you've got a natural gas feed coming into a boiler or a refrigerant line coming into a compressor, then you're going to try and have your gas sensor near that feed into that appliance. You're going to try and keep your sensors away from ventilation fans or intake louvers, because you don't want to trick the sensor by showing it fresh air when in reality the rest of the envelope may still have a certain amount of target gas concentration, and it's only seeing the fresh air coming in from the outdoors. And as you're placing these sensors, you're going to try and keep in mind that eventually they require service or replacement. So you want to make sure that they're accessible. So in a chiller room, if they're thinking about adding a second chiller, you want to make sure your sensor isn't right on the wall where they're going to put that second chiller, that type of thing. And then sensor coverage comes into play. How much coverage will a sensor monitor? How much area will a sensor monitor? And when it comes to the area that a sensor will monitor, you can kind of think of it like a light bulb. If you put a light bulb in the center of the ceiling, you're going to get 360 degrees of light. If that ceiling happens to be a huge meeting room or a huge gym, one light bulb in the middle of the ceiling, yes, it'll light it up such that you're not going to trip over stuff laying on the floor. You're not going to bump into people, but you're going to be a little hard pressed to go over and sit in the corner and read a newspaper. So just like spacing out light bulbs such that you have enough light to cover that large meeting room or a large gymnasium, you're going to place sensors out throughout an envelope that you want to monitor, such that you've got a decent amount of coverage and your sensors can react to the concentrations of target gas as the ambient air diffuses and convects and spreads that target gas throughout the ambient atmosphere. So in an underground parking space, parking garage, that can go as high as 10,000 square feet or a radius of 50 feet. Simply because you're not in an underground parking garage, you're not monitoring to workplace health and safety exposure limits. You're trying to balance exposure limits with energy saving when it comes to underground parking, because ASHRAE recommends, and most building codes state, that the only acceptable method to operate your ventilation intermittently in an enclosed space where there's a possibility of vehicle exhaust is to operate the ventilation with controls being CO and NO2 sensors. Conversely, if you're in an Amazon type warehouse or a Home Depot type warehouse where there's a lot of propane forklifts running around spewing out carbon monoxide, you're confined by the aisleways between the racking or shelving and product. So you're going to want to space your sensors out throughout those aisleways and the open area of the receiving shipping area of the warehouse, such that you can provide adequate coverage, and your sensors are no more than 80 to 90 feet apart. So here's an example of an underground parking garage. And remember I mentioned about a light bulb and the 360 degrees of coverage? I see a lot of plans, drawings come across my desk where the engineers place sensors on the perimeter walls. And just like a light bulb, if you take and you have that light bulb installed in the ceiling, you have 360 degrees of light. But if you put that same light bulb in a wall sconce on the wall, you now only have 180 degrees of light. So you've wasted a possible 180 that you could have had. So here's an example to show 180 degrees of coverage by trying to get your sensors a little further into the building envelope as opposed to the perimeter walls. So getting them on the support columns or any type of partial wall within that envelope that you're trying to monitor is going to take advantage of that 360 degrees of coverage, and you're going to use less sensors. Now, mind you, there's going to be situations, and here's a couple more examples. There's going to be situations where there are no perimeter walls. Some of these prefabricated, larger warehouse type buildings that span 100 to 120 feet or more in some cases I've seen, or a large airport hangar, you have no perimeter, you have no support beams. All you have is the perimeter walls. And yes, you can make use of the perimeter walls by not spacing your sensors that far apart, such that as the ambient air within that envelope diffuses and convects, there are more sensors to pick up on it. So you're kind of compensating for the area where you can't get sensors into. You're trying to take advantage of the natural diffusion and convection that takes place within that ambient, within that envelope in the ambient atmosphere. And just a couple more examples there. And so now you've got this little sensor element, and you've got a number of sensor transmitters, or maybe even a standalone self-contained system within that building envelope. But how does that actually work? How does that interface to the ventilation system and ventilate out any buildup of toxic gas? Here's a little example of a system approach wherein you have a controller, a centralized controller, and a number of gas detection sensor transmitters placed throughout that building envelope. And if and when a source of target gas enters that building envelope, and that target gas is picked up. It's constantly being seen by the gas detection system, just the same way a thermostat sitting on the wall is constantly monitoring the temperature of the ambient atmosphere within a building envelope. The sensor is monitoring the ambient atmosphere for the target gas that it was manufactured to detect. So it's real time. It's happening real time. And if and when a level or a concentration of that target gas builds up to a particular set point, in this case, carbon monoxide at 25 ppm, that information being constantly fed back to the controller says, okay, now I'm seeing 25 ppm, and I know, because I've been programmed to do so, that I now bring on the ventilation system. And the relay outputs, or a 4 to 20 milliamp signal or 0 to 10 volt signal coming into the ventilation or connected to the ventilation system, now activates the ventilation. And the ventilation will run until that concentration drops below the set point of 25 ppm, or whatever the particular set point for that particular target gas was. If for some reason or other that gas continues to build up, is not being ventilated out, perhaps a damper didn't open or a fan didn't turn on, but the gas continues to rise, maybe there's multiple sources all of a sudden and the gas continues to rise, then a secondary level, which we call a high alarm, can be set to notify responsible people. So a building manager or a maintenance manager, or worst case scenario, first responders, to come and take a look to see what's going on here and see why it's not being ventilated out. And you can have audible and visual alarms to alert the people within that envelope space that, hey, this gas has risen to a high level, it's time to evacuate. So you can control exhaust fans, you can activate audible and visual alarms, you can send information to the building automation system or a direct digital control system, or you can send a signal to an external monitoring station such as the building management team or the maintenance people or first responders such as the fire department. These are all the types of things that can be controlled from a gas detection system by either relay outputs, dry contact relay outputs, or by a digital information feed such as BACnet or Modbus, or a simple analog output, 4 to 20 milliamp or 0 to 10 volt, being fed to what you want to control, where you want to control it. We advocate a three-step approach to designing a gas detection system. If and when we are contacted to look at an envelope in regards to gas detection, we want to understand the application. Because typically we've been there and done that. If it's a swimming or a recreation facility with a swimming pool and a hockey ice rink, we know what gases in the past we have identified and what sensors would be required, and we can recommend an appropriate solution. Likewise, if it's a warehouse or an underground parking garage or any other type of application, once we know what the application is, we can easily identify the target gas, and we can make inquiries or show you how to make inquiries. Are there any other gases that may be present? For instance, a small chiller room in a low-rise building or a low-rise office building. Most of the time, that little chiller room is used for more than just a chiller room. A lot of times, the maintenance people will use it as a storage area to store all of their paints and solvents and cleaning material. In that type of application, we would not recommend a solid state refrigerant sensor, because the solid state refrigerant sensor can be set off by those solvents and paint off-gassing and cleaning fluid off-gassing can set off those solid state sensors. So we would definitely recommend, in an application like that, nothing but an infrared sensor, which is more specific to the refrigerant than to solvents and cleaning fluids. Conversely, in a situation where they're not going to use that chiller room for anything other than the chiller that's there, then a solid state sensor would be a more economical solution. Other things to understand, or other mitigating circumstances to understand about an application, is how large is the facility? How many square feet? That'll dictate the number of sensors required. What does the ventilation system consist of? How many fans are there? Are the fans controlled by VFDs? Are the fans controlled by 2-speed controllers? Are the fans controlled from the building automation system? And the building automation system is expecting information from the gas detection system to bring on the ventilation system. Are there regular washdowns? Is it a wet environment? For instance, fire vehicle, fire station, fire vehicle bays, where they wash them down inside in the wintertime. It's a wet environment. So we would recommend splash guards on the gas detectors for CO and NO2 that are installed in those fire engine bays. Is there an expectation of extreme temperatures? Is it going into a factory type application where they've got ovens and whatnot that cause the temperatures to fluctuate to somewhat of an extreme? Likewise, the humidity. Is there wild swings in humidity like there would be in freezer type applications, where there's constant movement from the production floor of food processing and into the freezers? That constant movement, you can see some pretty wild fluctuations in humidity simply because of the temperature drops or temperature changes between those two areas. All things to keep in mind when you're looking at specifying or designing or recommending some type of gas detection system. And identifying the target gas. Swimming pools, chlorine, ozone, and lately carbon dioxide. And to understand, this carbon dioxide is relatively new to the recreational swimming pool application because they're trying to control the production of chloramines in the ambient atmosphere. There's no gas sensor for chloramines. Chloramines are created by overchlorinated water in conjunction with the high humidity levels in the envelope above the pool water, and the activity, the amount of activity, the amount of people, because it's a certain amount of natural bodily fluids that assist in causing the levels of chloramines to rise. So what they're doing is they're taking high levels of carbon dioxide, and as the water goes through the chlorinator to be cleaned, they're then feeding in high levels of carbon dioxide to help maintain the pH level of the water and thus cut down on the chloramines. Or in applications in some areas, they're just switching totally away from chlorine to ozone, especially when you get into water being treated in zoos and whatnot, wherever they keep animals. They're not using chlorine, they're mostly using ozone. Likewise, ice arenas, ammonia from the chiller room, carbon monoxide and nitrogen dioxide from the ice cleaning machinery. And that ice cleaning machinery may be propane powered or methane powered. Either one of those create, those alternate fuels creates carbon monoxide that has to be monitored. And the fuel itself also is somewhat of a danger in regards to whether or not the fuel leaks while the ice cleaning machinery is parked in its little storage area or garage type area. If that fuel leaks out and there's a source of ignition, there's a possibility for an explosion or a fire. And refrigerants in refrigerant rooms, ammonia and carbon dioxide, and all the various refrigerants and even some of the newer refrigerants coming online. Even though some of those refrigerants, newer refrigerants, are simple asphyxiants, they still have to be monitored for the safety of the humans entering and exiting that room. So, just to recap, understanding the application, selecting the right product to build out a system. All of the gas detection manufacturers, including ourselves, manufacture a broad array of products to help you design and install a system that's going to meet the requirements for that specific application. And to recap again, parking garages, ice rinks, swimming pools, wineries and breweries, the hospitality industry. Now in the hospitality industry, most jurisdictions now have some type of regulation, whether it be in the building code or from the fire department under the fire code. The regulation in place is that anywhere that there's a CO2 tank, a tank of CO2 in an enclosed space, there must also be a CO2 monitor. These days, those tanks, through modern technology with regulators, the construction of the tank itself, and the methods for getting that CO2 into that tank, compressing it, there's a lot more CO2 in those tanks than there were a few years ago. So one of those tanks springs a leak and it'll fill up a room quite rapidly. And CO2 is an asphyxiant. And there's one of the questions I typically ask is whether or not people understand the difference between drowning or being asphyxiated. Well, with drowning, you have a fighting chance. Being asphyxiated is lights out. You don't even know what hit you. It's just like when you go to the doctor or the dentist for a procedure and they put you under, it's lights out. And depending upon how much oxygen has been depleted, you may or may not come back. So it could be a life-ending situation. So the rules are there. All enclosed spaces where there are where there is a CO2 tank being utilized must have CO2 monitors. Likewise, just over the last couple of years, battery charging. Anywhere where there's lead acid battery charging taking place, there must be a combustible gas hydrogen sensor there as well, because the hydrogen is created from the charging of lead acid batteries, and it floats up to the ceiling and it will collect there and build up if it's not being ventilated out. And it'll build up to the point where as soon as there's a source of ignition, you'll have a flash fire right across the ceiling. Laboratories, greenhouses, commercial kitchens, on both our West Coast and East Coast, the ferries, because the number of vehicles brought onto those ferries, and the fact that some folks during the wintertime will keep their vehicle running while they're on those ferries. They're being monitored for carbon monoxide, nitrogen dioxide, getting up into the lounge area or into the workers' quarters. And of course, welding shops and laboratories. So enclosed parking garages or repair facilities, bus barns, vehicle repair shops, ambulance stations, fire halls, NO2, and possibly combustible gas for fluids leak being monitored, and ventilation being utilized to vent out any unsafe levels of any of those gases. Recreational facilities with pools, target gases being ozone, chlorine, and carbon dioxide. Recreational facilities with arenas, methane or propane to operate the ice cleaning machinery, plus CO and NO2 created by the exhaust out of the exhaust of that ice cleaning machinery. Refrigerants, refrigeration rooms, ammonias, carbon dioxide, all types of other refrigerants. Typical example of a sensor system laid out or designed such that each chiller, whether it be different refrigerants in each of those chillers, or whether or not there's enough refrigerant that they just want to catch the leak at the soonest possible time, they can put one sensor per chiller. And of course have all the audible and visual and warning devices required within the facility, within the envelope and outside the envelope, so that people don't enter if there's unsafe levels, or people that are working in there are notified that there's an unsafe level and they should leave the facility. Wineries and distilleries. All the new microbreweries open up, the new micro wineries. Ethanol is the how they begin the fermentation process for the micro distilleries that are opening up. And ethanol is highly flammable, very unstable. So it has to be monitored, and it's heavier than the ambient atmosphere. So the sensor has to be down near the floor. And typically they'll classify it, that distilling room, they'll classify it, and they'll want explosion-proof fan and an explosion-proof sensor transmitter within that particular area of the envelope. And then with wineries and microbreweries, a large concentration of carbon dioxide is produced during the fermentation process, and that can be an asphyxia. Boiler rooms, because of a few recent accidents in public school system, now most of the public school systems throughout North America are mandating, or already have mandated, carbon monoxide and natural gas sensors in the boiler rooms, and notification appliances outside the boiler rooms and inside the boiler rooms. So just a couple of the news clippings that I was mentioning. And that's the end of the presentation. Any questions?
So in order to do questions, Ron, there's a chat bubble, not chat bubble, sorry, a question bubble on the right-hand side of everybody's screen. If you guys wanted to type in a question there, I can read that out, and then Ron can answer that aloud. There is one question in there right now that I can ask while you guys are thinking about any questions you may have. And the question is, what level of information does it report to BAS, i.e. just an alarm or PPM levels? That's from the control panel, Ron.
That depends on what you want. because it's real time. So think of your foot on the gas pedal and your speedometer. As your foot goes up and down on the gas pedal to increase or decrease your speed, your speedometer is moving up and down as well. So it's real time. So you can have as much information as you want fed back to a building automation system, either through a 4 to 20 milliamp signaling, 0 to 10 volt signaling, or BACnet or Modbus from our systems. And a lot of the other manufacturers offer additional information sharing through different protocols. But there's as much information there as you want. You specify what information you want, and we can show you how to get that information.
Okay. Next question. I think this one's gonna be hard to answer because of the complexity and scope of what we can supply. In fact, it's going to be impossible to answer directly, but generally, what is the cost of the system to supply? So
that's an easy one. That's an easy one. What's the cost of a lawsuit?
Yeah, it's a tough one to answer. I mean, directly.
What's the cost of a life?
Well, I think it's a fair question. The scope has to be defined a bit on that. So
typically the gas detection system is the smallest portion of the ventilation system. So even if the ventilation system only consists of 2 or 3 fans and 2 or 3 makeup air dampers, then you know that facility is small enough that the number of sensors that are going to be required is probably less than 20% of the cost of the ventilation system. That's a pretty good rule of thumb that over the 16 years I've been in gas detection, pretty much is accurate across the board.
Yeah, the other, if I could answer that a bit, generally it's the sensors. It depends on the sensor, really. I mean, a CO2 or an NO2 sensor might run you plus or minus $500 per sensor. But then if you start looking at explosion-proof sensors, you can be upwards of $2,500 for a sensor. The actual gas monitoring control panel, that also varies depending on how many sensors you have to monitor. If you're censoring 1 or 2, it's maybe $1,000. If you're censoring multiples, it can be upwards of $2,000, $2,500 for the panel itself. So you kind of have to take all the pieces, add them all together, and get your final price for the equipment. Okay, so the next question: would CO2 detection be typically required for a beverage manufacturer that has a CO2 tank external to the building with piping to an indoor carbonation machine?
Yes. Yes, and I think that if that's not already in the local building code, the fire department will step in and when you go for occupancy permit, the fire regulatory body will say, you've got CO2 being fed in here, you have to have a CO2 sensor. I've run into this over the past, it has ramped up over the past 24 months. There have been a number of actual deaths.
Okay. Next question. What is the code requirement for entrance to chiller rooms? Does each entrance have a remote panel with strobe light with siren and outdoor only strobe light?
No, the actual code, the Canadian code, states that it must have an audible and visual notification appliance, and that's it. an audible and visual notification appliance. So that can be as simple as a horn strobe, or that can be as complicated as a remote display with a horn strobe. That's up to the engineer of record or the engineer having jurisdiction, what they want. But the code states simply a notification appliance, audible and visual notification appliance.
So is that inside the room or outside the room, Ron?
Outside the room and inside the room.
Okay. Next, I think that answers the question. What is the next question? What is the code requirement for entrance? Sorry, I just read that one. Right. Next one. CO and NO and NOx come out of engines hot. They change the density as they cool. Where to locate the sensors?
Okay. NOx is a slang term for all of the oxides of nitrogen that are produced from the incomplete combustion of diesel fuel. Most of those oxides of nitrogen are not toxic to human beings. There are two that are. Of those two that are, nitric oxide and nitrogen dioxide, nitrogen dioxide is not formed in the exhaust. It's the oxides of the nitrogen combining with the ambient atmosphere such that a molecule of nitrogen oxide and a molecule of oxygen now create NO2, O2, the oxygen in the ambient atmosphere. The molecular weight of nitrogen dioxide is 1.5 times the molecular weight of the ambient atmosphere. Heat will not change molecular weight. Okay? Molecular weight, the only way you can change molecular weight is to change the molecules themselves, and therefore you no longer have that particular gas, whatever that gas was. Okay? The effects of heat on a gas is a change in density. So the warmer it gets, the density, it fills the room faster. It has not changed its molecular weight. If your sensors are being installed to protect people, and typically NO2 and carbon monoxide sensors are installed to protect people, you want those sensors in the breathing zone where the average person is breathing. Nitrogen dioxide and all the other constituents of diesel fuel are being very carefully monitored and watched by the Center for Disease Control and all of the sister organizations in all the different countries, because over the last 15 years, they've been on this campaign to clean up the diesel, to get all of the particulates and some of the more toxic constituents out of diesel. And this clean diesel has been a very successful campaign. Most people that are middle-aged now, they remember back 10, 15 years when the black plume coming out of all of the transport trucks on the highways and roadways was thick, coming out of just about every diesel vehicle. Now they're few and far between. So during that period that they cleaned up diesel exhaust, they did not see the decline in reported rates of cancer that they expected to see, especially in the mining industry, in the rail industry, and in the long haul big truck industry. They did not see the decline that they expected to see. So they said, okay, there's more to this than just all that stuff that we've already cleaned out of there. So now we have to monitor all of these other constituents to see what other constituents are also contributing to the rates of cancer reported in those industries where diesel fuel is used extensively. So they're all being watched. And that's one of the reasons why the International Mechanical Code a few years ago changed the code to include NO2 sensors for any enclosed space where there's a possibility of vehicle exhaust. I hope that answers your question. If not, I'll be more than pleased to provide you as much information as I myself have available.
So I think that was a very good long response, but I think the answer where to locate it is 3 to 4 feet above finished floor. Is that correct? Both CO and NO2.
Yes.
Okay.
Yes, no question.
Yeah, because you want it in the breathing zone to protect the occupants.
You want to protect the people. That's exactly right. You don't want to protect the ceiling.
So that's that concludes the first of our isolation intelligence webinars. I appreciate everybody coming out to listen, and I hope you all had got some information and found it useful. I will make this presentation available. If people want it, just send me a quick note and I can get that over to you. And again, appreciate everybody's attentiveness and hope everybody's keeping safe.
And I thank you very much.